I'm here, guys. How are you doing? I'm letting people in. So,
Hello.
hey, Haley. I got Haley. I got Stephanie. I got Anai.
Hi.
Got Tori. Hey, everybody. I got Bree coming in. Okay. Let's see here. Michelle. We'll wait a couple more minutes here. Here's Michelle. She's on officially. Oh, there's Bree. Bree, I see you today. Usually I just see your initials. How are you doing?
I'm good.
All right.
My connection isn't that great, so I usually turn
Yeah.
off my video to make it better.
Yeah, I got bumped yesterday off one of my classes too. I feel like panic. It's like, oh no, I got to get back in fast. All right, guys, let's kind of take a breather here and assess where we are. Yesterday we started learning about these optimization word problems. I didn't do many examples. That's what I'm going to do today. I'm going to do as many examples as I can today and let you loose on the homework again for tonight and probably the next night too. This is the last thing on the test, and I do not want to do anything new this week, okay? I have put the review sheet on Moodle, so make sure you're starting to look at that. We'll spend time going over the review sheet, definitely probably start tomorrow and go through Thursday on that. And Friday, we'll have an optional meeting period also at 11 if you just want to work problems or whatever. I will try to get out sort of a key to the problems that at least that I've written on that sheet, so you'll know what to look at. And if you have any questions, I would start working on that if you hadn't already, a little bit all along. As I said yesterday, the whole big first chunk of this is all about graphing. And we did the same things over and over and over again. We took derivatives, we looked at number lines, we found increasing, we found decreasing, blah, blah, blah. We did all of that. That's the main focus of this test. We added asymptotes with it all along. And then we had the business optimization, which we had a quiz on. Everybody did pretty well on that. And I think we got mistakes corrected on that. And then this last piece is just another kind of optimization. Some of which can be considered business, and some of it's not quite as obvious as that. Okay. All right. Does anybody have any questions for me before I get started? Before I share my screen? If you have homework questions, I'll take those as well. I didn't assign a whole lot of homework because I didn't do a whole lot of examples with this. So I think I want to do some examples first, and maybe it'll remind you of things you saw in those few homework problems that I gave. That'll kind of help you to sort of know what to do with this process. This is not an easy one for me to teach online. There's some things I'm going to want to show you, so I'll let you know when you need to be looking at me on the screen to do some things that the problem asks us to do, and see if we can't be a little more interactive. That's what's hard for me about this, is that it's not as, I can't see you. I can't see the bad look on your face all the time when I do something you don't like, or when I can't congratulate you when you do something good and I can't see it. Okay, so we'll try to break in if you don't understand things that I'm doing today, and then we'll maybe look at some of the homework. All right, let me share the screen here. This is where I got into trouble yesterday. I want to see what happens today. Okay, that's good. Right.
For the homework, I was just wondering if number one was similar to the one we did yesterday in class.
Yeah, you're talking about one in the book, Haley? Is that what you're talking about, or one on the sheet?
I'm talking about the one on the sheet.
Oh, wait, who's talking to me? I'm not sure it's Haley. Who is it? Okay, Anai. Okay, one on the sheet. Okay, that's good, because I actually think that may be the first one You mean the one under the homework, I think. That may be the first one. Is it about the shed and the and all of that?
Yeah.
Okay.
So I did it similar to the one we did yesterday in class.
It is similar. And I tell you what, I'm going to do one more example like that, and then I'll do that one, okay? Because I think these fence problems are prolific through all of this stuff. So that'll help us with some of those. So let me do. I'll do a couple of I'll do an example, and then I'll do that one. She's asking about number 1 under the homework that said a rectangular garden is created using 600 feet of fencing. What I've done on this sheet for the lecture is try to type out the problems that I wanted to do, and then I'll fill in as I need to go. But it's another fence problem, and then I'll look at what Anai's asked me. Let me get Jennifer in here. Let's see before we go. Okay, that's good. I don't want to chat. Okay, so guys, what I've got a problem here that it's another fence kind of problem. It changes up things a little bit over what I looked at yesterday, but it's got I can't get this thing out of my way. Hang on a second. There we go. That's better. It says a rancher has 100 feet of chicken wire. We're starting with 100 feet again. Now, when you see that he has 100 feet of wire, that's going to be your perimeter. I mean, that's what you've got to go around whatever enclosure. And he wants to make a rectangular enclosure again. One side will be against the side of a barn and will need no wire. What dimensions will maximize the enclosed area? Now, let me say, first of all, that a good picture's worth 1,000 words, and you probably can't do these problems without writing a decent picture, and you'll get at least a few points for drawing me a good picture, okay? So when I look at this thing, now what's on display here is my kindergarten level of art, but whatever, that you guys will be able to draw better pictures than I will most likely. But what I'm looking at here, let's just say we got a barn right here. Okay, so that barn is just sitting out on the farm somewhere, okay? It then says they want to make an enclosure, which is rectangular, but they're not going to need, and they want it up against the side of the barn. So here's what I'm going to do. I'm just going to say, okay, it's a rectangle. Oops, that's a bad rectangle. But anyway, it looks like a rectangle. Actually, it's so bad, I'm going to erase it. It doesn't look much like a rectangle. Let's try again. I'd like to have straight sides on my rectangle. How about that? That's better, okay? Now, it says I don't need any fence here. So the only place I'm going to use fence is on these opposing sides and that long side. And I don't know how long they are. That's what I'm trying to find out. So I want to maximize area. So I'll just write out, when I attack a word problem, there's almost, when you read the whole thing, there's almost too much to bite off in one chew, all right, or one bite. So what we want to do is sort of sort through things and write things as we go. And usually when you look to the end of the problem, you'll see, well, where do I want to end up? Well, where I want to end up is to maximize area. So I need a function for area. Now, we already know all the calculus for all of this. We maximize things by taking their derivative, setting them equal to 0, that whole thing. The difference in these problems is that you got to come up with the formula. Okay, it's not just thrown out there and said, okay, what's the maximum, what's the local max on this function? You got to figure it out. So we don't, most importantly here really probably is we don't know what size this thing, we don't know what size this thing needs to be. So I need to label some things. I'm going to label the sides, these two sides, as X, and this one is Y. Now, you don't want to label them all X because you don't know it's going to be a square. And I don't want anything over on this side because no fence goes over there. All right, so I want to maximize area. So let's review our geometry here. How do you find the area of something like this? If I've got it labeled like this, somebody tell me what the area is. What's the area of that as it's labeled?
X times Y?
Yeah, it's X times Y. I mean, if I had a 2 and a 3, you'd say 2 times 3. It's just a generic thing for area. So that's what I'm trying to do. Now, as you write things down here, not only are you accumulating some points, you're actually, you're getting closer to what you need. Now, you're going to go back up to the problem. And I will say, if you haven't read a word problem 3 or 4 times, you've probably either given up or you hadn't sucked enough out of it to get what you need. Okay? Do not give up. Keep going back and reading it. The thing we haven't used is the fact that the rancher has 100 feet to enclose the area. Now, the 100 feet is the perimeter, guys. So if I had to write down one other thing that I know, what's 100 going to be? If I look at this generic picture right here, I look at that generic picture. Perimeter is all the way around. It's not area, it's all the way around. As I have it labeled, tell me what the perimeter is going to be. Just generically, what's the perimeter going to be?
2x plus y.
Yeah. Guys, we got an X there, we got an X there, we got a Y there. So 2X plus Y. This is very similar to the one we did yesterday, except we don't have any fence over there. But it's going to work the same way. Now, here's the deal. You've kind of written down everything you can find. We want to maximize area. As I said yesterday, the functions you guys have been maximizing are in terms of one variable. So what you've got to do is either replace X in terms of Y or Y in terms of X.
I have a question.
Yeah, Haley.
So, how did you know to make, like, when you drew the picture, how did you know to put the X twice and the Y once instead of, like, the Y twice and the X once?
Okay. In other words, you're asking me could I have put Y and X here?
Yeah.
I could have. So it'll come out, it'll wash out in the end. You'll find out what Y is, and Y would be the short side then instead of X, and X would be the long side.
Okay.
It doesn't really matter. Okay. Right. That's a good question. I could label them anything I wanted, A and B, or B and A. It doesn't matter as long as I get some generic idea what's going on there. Okay, so what I need to do is put this in terms of one variable. So that means you need a link between X and Y. This thing about the perimeter is the link. And I think it's probably easier to solve for Y in terms of X here. So I'm going to say Y is pull that 2X over to that side is 100 minus 2X. Y is 100 minus 2X. Now, what I'm going to do with that, the whole point of that was to write this thing right here in terms of one variable. That's what I need to do. And some problems don't start like this. Some problems don't have two variables in them, and you can just go forward then, taking the derivative and so forth. But before I can take the derivative, it needs to be in terms of one variable. So I'm going to rewrite A in terms of one variable to be X times 100 minus 2X, which is what Y was. I'm going to multiply it out, so it'll be a little easier for me to look at in a minute. Right there, I've got an equation in one variable that I'm trying to find a maximum value for. Now, guys, you are 3/4 of the way home here when you get this. This is the hardest part of the problem, where you're going through and you're trying to figure out what the equation is you want to maximize. And that's where all the words come in from the problem. So it's pretty easy now. How do I maximize a function? One thing I do, or the first thing I do, is I take the derivative. What's the derivative of that thing right there?
100 minus 4x.
104 minus 4x. Guys, I want you to take, I want you to find the critical numbers and draw a number line. I've got to go grab something for a minute. Hang on a second. Just find the critical numbers and make a number line on that. Hey, Dad. I'm teaching, okay? Yeah. Okay, guys, let's see what you did. Somebody tell me what the derivative is. What's the derivative? You're looking at the derivative of that thing right there. Cut your mic off cut your mic on and tell me what the derivative is.
100 minus 4.
100, because the derivative of 100x is 100, and then minus, use the power rule here, and that's minus 4x. All right, good. So we're doing the same thing we were doing if we were going to graph this thing, guys. Critical numbers are where this is 0. Somebody tell me what the critical number is. That's actually
25.
pretty easy. What is it?
25.
25. Okay, it's 25. So if we look at that number right there, and we say we're going to test left and right, because we really want to know if this is a maximum. So if I test to the right, for instance, suppose I plug in 30, 100 minus 4 times 30, that's 100 minus 120. That's going to be a negative number. That tells me it is decreasing over there. To the left of 25, and guys, on these kind of problems where we're actually applying something, we're not going to have negative fence. So I can just say, I'm going to stop over there at 0. So maybe I'll try 20. 100 minus 4 times 20 is 80. 100 minus 80 is positive. That's exactly what I've got there. I've got a max there. Now, let's finish up the problem because everything's done. All you have to do is state the answer. A lot of times, guys, if they ask you to maximize something, you're pretty sure of this. A lot of times I'll just find the critical number and stop at this point. Because if they ask you to maximize it, it's a pretty good assumption that you're going to get a maximum there. But I'm just showing you that it's the same thing we're doing with graphs. So this was X. So when I go up and label the picture, I say, okay, X should be 25. So now, what Haley asked me a minute ago, would it matter if I put everything in terms of Y? No, you would have gotten Y equal 25. Now, how do I find out what Y is? All right, I know that the short side of that enclosure is 25. How do I find out what Y is?
Well, if all of them have to equal 100, wouldn't you just minus 50?
Yeah, good. That's exactly what this thing says right here, right? There's the connection. You knew it all had to add up to 100. You've already got 50 on these sides.
So Y would be 50.
Right. So Y would be 50. Everybody else understand what I did there? The other place you could go to find that is right here, because if you know what X is, this will tell you what Y is.
So there's a local max at 25.
Not only is it local, it's absolute. Okay, because it's going up. There's nowhere else that's any higher than that. Okay, so that says if we want to maximize the area, we'll make this enclosure 25 by 50 feet, feet. Now, I'm going to ask you one more question, and I want to make it analogous to when you graph something. When you tell me what a maximum or a local max or whatever is, when you're graphing things, you say the local max is the Y value. Okay, the local max is the Y value. Where it occurs is the X value. Now, I'm going to tell you that these places are where that maximum area occurs. But what if the farmer turns around and says, well, what is the maximum area? Well, that's not hard either, because you got the dimensions on there. I mean, you say, I'm going to make the dimensions this. How do you find the area from that, guys? What's the actual maximum area here?
50 times 100 or 50 times 25?
50 times 25, okay? Because we know that area is equal to length times width. So once we know the length and the width, we can say what the maximum is. So that's actually the maximum value of the area. And that's going to be, how much is it? 1,250 square feet, I think. 5 times, 1,250 square feet. You could also find that, again, by going back to the original function. Remember how we went back to the original function to find out what the Y value was, what the high Y value was? You're going back to the original function here. It's exactly the same thing.
But where the problem just asked for what dimensions, you would just put 25 and 50, right?
Yeah, I mean, if all it asks for is what dimensions will maximize the enclosed area, you really only need to give me label the picture would be enough. It would also be nice if you put some units with it, please. If I can use feet like that, or I can say feet. So the answer to this question is 25 feet by 50 feet.
All right.
Typically, I might have asked, okay, what is the maximum area? And you'd finish answering it that way. Everybody see what Haley's asking? I really only asked, what are the dimensions of the yard? There they are. Now I sort of added on that thing about what's the actual biggest area. Okay, is everybody okay with that one? All right, let me address, I'm gonna undo one I did yesterday so I can address, and this is on the video. I think I got y'all's video online so you can see it again. I'm gonna undo this and I'm gonna answer a nice question about the homework problem, the one with the gate and so forth. So we need to show you how important it is to draw a good picture. And let me get rid of this. So we're looking at which one was it? Number one on what page? Where is it? It's back on. It was one of the ones I assigned in the homework problem.
It was on the handout.
Oh, it's the one on the handout. Oh, okay, not in the book. Okay, that's fine. Great, we can do that too. I'll go back and look at that. So let me finish erasing this and take a breather for a second while I get it all erased, and I'll bring the problem up. Okay. This example is a good one. The one here is a good example of how you got to draw a good picture. All right, let me get all that stuff off so I can get a page here. Had all my other examples typed out. This one I didn't have typed out. Okay. Sometimes when I'm playing on this pad, I feel like I'm back in kindergarten. Not that they had these pads when I was in kindergarten or anything. Okay, so let's roll back to the handout and look at the problem. So the handout said, and this was the first one under the homework. The handout said a rectangular garden is to be created using 600 feet of fencing. You see the similarities here. That's got to do with the perimeter. At one corner of the garden and at right angles to each other will be a 20-foot shed and a 20-foot gate. Now, the implications there, guys, are that you don't need any fence where the gate is, and you don't need any fence where the shed is. It's sort of like the barn in this thing. It says, find the dimensions of the garden of maximum area if no fencing is needed for space occupied by the shed and the gate. All right, I need a decent picture here. And then I'll start trying to figure out what it is I need to do with the calculus. So I've got this rectangular enclosure. But I'm gonna, oops, let's fix that. I'm gonna stop a little short. Dang it, wait a minute, messed up everything. I'm gonna stop a little short when I'm drawing it and leave room for the gate and the shed, okay? So let's let this be the gate right there. And we'll let that part right there is the gate. And that part right there is the shed. Now the gate is gonna occupy 20 feet and the shed's gonna occupy 20 feet. Shows that. So I don't need any fence there, and I don't need any fence there. Okay. So guys, drawing the picture is the key here. And I don't know how clear that was to you, but when it says the gate and the shed are at right angles to each other, all that means is it's in the corner of this rectangle. That's all it means. Okay, so at least try to draw something or you're going to have a hard time getting started, particularly in these kinds of problems. Now, we wanted to maximize area again. Now, the fact that it has a gate and a shed there really isn't going to affect the area. The area is still going to be X times Y. And I don't really care which one I let X and which one I let be Y. I'll just say XY right here. All right. Now, so the area in this one is the same as it is for any rectangle. It's X times Y. Now, how much fence did we have, guys? Look back at the problem. How much fence did we have to use in this one?
600 feet.
600 feet. All right, now let's go back and label the rest of the sides on this thing, because we know that those sides have to add up to 600. And this is the one that makes this one a little bit trickier than the other one. That's a whole X side. That's a whole Y side. How much is that right there?
Would that
What
be
is
X minus 20?
Say what minus 20?
Would it be X minus 20? Or
Well,
Y?
look, I'm pointing to this side right here. So that's actually taking 20 away from Y. Does everybody see that? If I was pointing at this long side right here, I took 20 away from Y. So it'd actually be Y minus 20. But you're giving the answer to one part, you're giving another answer that's correct.
So the top one would be X minus 20.
Yes, the top one. So that little piece right there will be Y minus 20. The top one, see how this bottom was X? That would have been the same size as that. So I'm taking away 20 for X for this little piece right here. So X minus 20 is that. Okay. So guys, do not be discouraged with these word problems. You've got to attack them. That's the only way you can conquer these things. You draw a picture, you write down what you know. What I know so far is that I'm going to use X from right here, Y from right here, Y minus 20, that's going to be using up part of my 600 feet of fence, plus X minus 20. These were the shorter sides because of the gate and the shed, and the other sides were the long sides. So if I write that, I'll have, and combine all this stuff, I'll have 2X plus 2Y minus 40.
Yeah.
Yeah. Okay, Naya, this is your question. You okay so far? Understand what I'm doing so far?
Yeah, I think I just messed up on the X minus 2 and Y minus 20 part.
Yeah, it's not a 2, actually, it's a 20. I don't know what happened there, but anyway, it's a 20 because I'm taking away 20. And that's how you, some of these problems you get a little more practice with doing them. You'll sort of see how they get set up. But try not to be discouraged by the word problem. One of my favorite cartoons is, and I'd show it to you if I were there. I don't really have it with me, but I don't know if you know who Gary Larson is, but he writes really funny science and math cartoons. And it's got a picture of some guy waiting at the gates of, unfortunately, hell. And the devil's standing there, and he's saying to this guy, "Here, I'm going to show you hell's library." And on the shelves are books labeled word problems, story problems, more story problems, more word problems. It's just a whole bunch of shelves full of word problems and story problems. And underneath it says hell's library. Now, I have a feeling that's the way most people feel about word problems. You're like, oh my God, it's a word problem, and just kind of shut down. Well, in fact, everything that happens in the world is a word problem. Okay, it's not set up nicely for you necessarily. Okay, so let's get back to here. If I move the 40 over to the other side, just to make it look a little better, it's 2X plus 2Y. And then I can divide by 2 and make it look even better. Do as much as you can. So right there, I have a connection between X and Y. Now, remember that I wanted to maximize the area again in this one. I wanted to maximize the area. It needed to be in terms of one variable. So there's my connection between X and Y. All this stuff about labeling the picture and using the perimeter got me this equation. So Y, will be here. So Y, if I solve for Y, it would be 320 minus X. I'm going to take that up there and put it in for Y. Knowing the perimeter and connecting X's and Y's that were on the sides allow you to do that. Again, you are almost home when you get to this point. Because if you say, if I multiply it out, I get 320x minus x squared. Make that look a little better. Get 320x minus x squared. Okay. There's the function I want to maximize. What's my next step?
Take the derivative.
Take the derivative. Take the derivative. That's why we're in calculus, to take derivatives. So a prime is 320 minus 2x. And I find the critical number right there. And I solve that equation that says 2x is 320, which says x is 160. And again, if you want to test it, guys, you can put 160 on here, but you will see that what you'll get is a maximum there. You'll get decreasing on the left and increasing on the right. Okay. So I'm going to label what I got. X is 160. So that full side is 160. That full side is, oh, how do I find that? Y is 320 minus 160. Okay, we knew that from right here. So I wind up with another 160 right here. So Y was 160. How much fence are you going to use on this short side right here, guys?
140.
140, because it was the whole X side minus the 20 for the gate. So that's 140. It's you see how important it is to get a picture, because then you can go back and see what you were trying to find. The Y was 160. So that side is also 140. Okay. Bless you.
Thanks.
All right, now, how could we check it? We could add up all the sides. What should all the sides add up to, guys? How much fence did the person have?
600.
Person had 600. So 160 plus 140 is 300. Another 160 plus 140 is another 300. We get 600. And the dimensions of this thing should be, you really would say 160 by 160. Those are the dimensions of the rectangle. And then you got to take the shed out here. Shed in the gate. Okay.
So you would just say 160 by 160.
Yeah,
and
you'd say 160 by 160. In effect, it is a square. All right, but just the whole point is you don't have to. You could make these sides longer because you don't have to use as much fence there. Well, not longer in a sense, but you don't have to use as much fence there because of the gate in the shed. Okay. Questions, anybody? So a picture,
These are hard.
they are hard. They're not as easy as just somebody just throwing you out a function and saying, take the derivative and find the critical numbers. You really got to look at what you're doing. You got to label things. I will give partial credit here, guys, as we go down through this stuff. Draw me a picture, write me what you're trying to maximize, see if you can find a connection between these things, using the perimeter, those kind of things. So, I mean, but really, if you make those connections, you should be able to get to this equation right here. Okay, don't give up. All right, I'm gonna show you. Let's see. I'll show you another one. This doesn't have a fence in it, and you can't draw a picture, but it's actually not that hard. Okay, it says find two numbers whose sum is 10 and whose product is maximum. And this might have been one of your homework problems as well. So find two numbers whose sum is 10 and whose product is maximum. Well, first of all, guys, we got to have some variables. What are my variables going to stand for in this problem? Read the problem and tell me what I need to find. What do I need to tell her in the end? What do you got to tell me in the end of this problem?
So something plus something is 10.
Yeah, something plus something. What Haley said is something plus something is 10. I got to give a name to those somethings. So I don't know what they are, so I'm just going to call them X and Y. Okay, so I'm going to let these two numbers, and your hint here, guys, is find two numbers. Well, I'm going to let those two numbers be X and Y. I'll let those two numbers be X and Y. All right, now, what do we know about those two numbers? Keep reading. As I said, if you have not read a word problem, if you've not gone back to it about 3 or 4 times, you're not doing what you need to do to avoid quitting, basically, okay? Then it says find two numbers whose sum is 10. Okay, everybody write, just take a second to write, what is that? If the two numbers are X and Y, what does it mean to write their sum is 10? Okay, write down what it means for their sum to be 10. Well, sum means plus. So there's a piece of the puzzle. I don't know what to do with it yet, but there you go. There it is. That's sort of like giving you the fence that you've got to make with this thing with. All right, but it's two numbers that add up to 10. All right, what am I trying to maximize here, guys? If I want to write an equation for what I'm trying to maximize, there's only so much more left to read in this problem. It's actually pretty short.
So
But
the product is like the answer, and that's what you're trying to make?
yeah, the product is what you want to maximize. How do you write the product of X and Y? I mean, what do I mean by the product of X and Y?
So you
Anybody?
would minus X and then by equals negative X plus 10?
Not yet, not yet. I'm kind of done with this for right now. But if I said maximize the product.
They're just multiplying X and Y.
Yeah, you just multiplying X and Y, aren't you? That's a product of X and Y. So the product equal X times Y. In this case, that's kind of like the area, okay? But the product of two numbers is X times Y. Okay. Now let's ask while there's the pieces of the puzzle. I'm trying to maximize this. That's the thing I want to differentiate. Now I always get, well, I'll say that in just a second, but I need this in terms of one variable. Now here's where, Haley, here's where you need to come in with the other piece. If I need to find this in terms of one variable, usually we're used to looking at it in terms of X. How do I know what Y is? Is there anything I've written down here that tells me what Y is in terms of X?
Yeah.
Yeah, there it is. So when I look at this, I'll get P equal X times 10 minus X. And if I multiply it out, I'll get 10X minus X squared.
Then you take the derivative?
Yes, see, we've done the hard part now. Now let's just take the derivative and see what happens. If I take the derivative, it'll be 10 minus 2X. What is the critical number?
5.
Yeah, it's 5. You're just looking for where that's 0, so I just solved it. We just solved it. To the right of 5, it's negative. To the left of 5, it's positive. You're definitely going to have a max there. Okay, plug in some test points and you'll see that. That says that my number X here is 5. Now, if one of the numbers is 5, and I know they add up to 10, what's the other number?
5.
5. Yeah. So let's talk about what we've done. What is the maximum product? If those are the ones that give me the maximum product, what's the maximum product, guys?
25.
25. Yeah, that's right. Okay, good. So The maximum product is 25. I went here to say that. Back to the original. Maximum product is 25. Now, let me show you sort of what we've done, just to give you a little more idea here. I could have picked two numbers, 2 and 10, 2 and 8, that added up to 10. Well, what's the product of 2 and 8?
16.
16. They weren't the ones that gave me the maximum product. I could have used 1 and 9. They add up to 10, but 1 times 9 is not as big as 25. I could use 3 and 7. Okay? If I use 3 and 7, they add up to 10, but 3 times 7 is 21. Not as big as I can get. That is as big as I can get. Okay? And what you're really looking at is a parabola here. Look at this thing right here. It's a parabola that turns down. Its peak is at x equal 5 and 5, 5. And the product you would get there would be 25. Question about that one. Let's look at a little bit different one here, guys. Now, let me, as rudimentary as my art skills are, I sort of have to draw a picture here. And it's about the only 3D picture I can draw, but we're going to read the problem and see what we need on this. It says a manufacturer wishes to minimize the cost of a box container. Ooh, I left out a word, made from thin sheet metal. So minimize the cost of a box container made from thin sheet metal. It doesn't matter what it's made of. Whatever. All right. The container will have a square base and a top and a bottom. Obviously, it's going to have a bottom. It's got a top and a bottom. And must have a volume of 36 cubic inches. The top and the bottom cost 12 cents per square inch, and the sides cost 9 cents per square inch. What dimensions will minimize cost? All right, now, here's how I draw a box. Does anybody, I mean, it's about the first thing you learn. Somebody wants you to draw something in 3 dimensions, or look, you're drawing it on a 2-dimensional surface, unfortunately, like a chalkboard or this thing I've got right here, but it's got to look like it's got 3 dimensions. Does anybody know how to draw that? Are there any art people? And there may not be any art people in here, I don't know, but how do you don't have to be an art person to know this. Can anybody draw what looks like a 3D box? Anybody know how to do that? Anybody got one drawn on the paper? If you do, I want you to hold it up. Michelle, you know how to draw that? You're kind of looking at it.
Like
Michelle, that? Haley, hang on, let's see. I can't see. Pull it up a little bit. I got a little bit. Pull it up. Okay, all right. Haley's got a picture of it. And let me ask her if this is the way she did it. I got it. I think you got it right. Okay. Here's the way I draw a box. I draw basically a square.
Yeah.
And I kind of overlap a square.
Yeah, that's how I did it.
There, okay, guys. So here's your first lesson in 3D art. One of the things I wish I'd taken in grad school or in college or anywhere is a technical drawing class, because it really would have helped my teaching a lot. It's about the only one I can do. Once I draw that, I'm going to connect these edges right here. And you got a box. Okay? So draw the 2 squares and then connect the edges. Now, let's think about how we would label this box based on this picture here.
Well, how did you know that it was, how did you know to draw a 3D instead of a normal?
Well, you can't keep much. You want to make, it just says, because it says a box. That's really how I knew there. Okay. I do have a problem later on we'll do, maybe tomorrow, that uses just a sheet of paper to make a box. If I have time today, I'll look at that one, but I'll look at it tomorrow. But it's got to look like that. And another way I knew is because it said it has volume And you only talk about volume when you have something that's 3D, right? What's the volume of a box, guys? Anybody? What's the volume?
Is
of a
that
box?
length times width times height?
Yeah, it's length times width times height, right? Length times width times height. Now, let's label this thing like that. Now, there's one thing I need to remember. It has a square base. So if this is the length and that's the width and that's the height, what can you say about the length and the width? I mean, if it's a square base, the length and the width are the
Same.
same, right? Okay. So I'm going to say, I'm going to call this X, X, and Y. So that's what I'm doing. Length, width, height here. I let the length and the width be X, and I let the height be Y. So that's what I did there. Now, this picture is really going to help me because otherwise I can't see what's going on. Let's read the problem again. It says it's got to have a volume of 36 cubic inches. So right here, that's volume right there. So 36 is X squared times Y. Now, that's not what I'm trying to maximize or minimize. That's what I'm saying. It's got to have that volume in the end. Somehow that's going to help me find something. Now, let's go back to the problem. The top and the bottom cost 12 cents per square inch. And the sides cost 9 cents per square inch. What dimensions will minimize cost? Okay, this will get you a point too. Tell me what you're trying to minimize. You're trying to minimize cost, right? That alone will sort of lead me down a path where I might get somewhere. All right, let's go back to the problem again. I just keep going back because I kind of forget what it said. So just keep going back and picking it out. The top and the bottom are more expensive. They have to be more, sturdier or whatever. So what's the area of that bottom right there, guys? Now we're looking in 2 dimensions. What's the area of the bottom?
X times X.
Yeah, does everybody see that? Because it's length times width. And if my box is worth a darn, the top's the same size, right?
Yeah.
So if I look at the top, X squared is the square inches there. If I look at the bottom, X squared is the square inches there.
And then
Now, how much did it cost per square inch?
12 cents.
12 cents. Okay, go back up there. That's how many square inches you've got in the top. So it's 12 cents times that square inch. You can put the decimal in it if you want to, guys, or you just leave it in cents. Same thing with the bottom. Now, here's something that's a little bit harder to see, perhaps. We got to worry about the sides. Okay, now, the first thing I want you to tell me is how many sides are there?
2.
How many sides are there on a box? Anybody? 4, right? 4. If I had a box here, I'd hold it up. Yeah, there's 4 sides on a box. Now, let's look. Okay, there's a side in front, there's a side in the back, and there's sides on the side. Okay? Front, back, side, side. Each one of these has dimensions X times the Y, right? So that's X, and that's Y. So the sides are X times Y, square inches. And the back is X times Y, square inches. They sort of look like a square. I didn't draw this very well, but I have them labeled so I can see that back side is going to be X times Y and the front side is going to be X times Y. So I have 4 sides whose area is X times Y, and they cost 9 cents per square inch. 9 cents per square inch. Okay, the hard part of this is done, but I'm gonna leave you to finish it because I'm gonna do a couple more steps here. We're sort of running out of time, but I have to assess this whole problem and say, well, what is the size of the box? I've got top, bottom, sides, and I know how much each square inches of those cost. I'm gonna simplify this. It's 24x squared Putting those two together. This is 36 XY. Okay, that's the total cost of the box. Now, as with the other problems, I need to write this in terms of one variable. I can't differentiate it if I don't have it in terms, fully in terms of X. Your connection for that is right here, guys. Look at it. Y is 36 over X squared. So when I put that in, plus 36X times 36 over X squared. Now, what's anybody got a calculator real quick? Tell me what 36 times 36 is. I never know where my calculator is. What's I'm going to go a little further and let you finish it up, okay? That's C equal 24X squared. What is 36 times 36?
1,286.
1,286.
6.
Yeah, and then we know that X over X squared would leave me an X in the denominator. So if I simplify that last term there, X over X squared, and then 1286, I'll have plus 1286 over X. That's the function I'm trying to minimize.
It's
Now,
96.
Is it 96? Okay, thank you.
Yeah.
I didn't hear that. Thank you. Good. What do I do once I've got a function to minimize here, guys? Answer me and we can have lunch faster.
Find the derivative.
Find the derivative. How am I gonna, that's easy to find the derivative of. What will I need to do to this before I find the derivative? It's over X. What do I need to do with this thing? Remember back to test 2 where we were taking derivatives. We need to write this as X to the minus 1. If I want to take the derivative of that, it'll be 24X squared plus 1296 X to the minus 1. Now, I want y'all to finish this one up. I want you to take the derivative and see if you can find the critical numbers, okay? You're going to have to mess with some negative exponents, and I introduced a negative exponent here in order to differentiate it. When I'm finding the critical numbers, I'm probably going to want to get rid of the negative exponent. Now, be careful when you do these things. A lot of people think they've done so much work when they get to here that they forget about the calculus. We haven't done any calculus yet here, guys. We got to take the derivative, okay? So this is where we'll start tomorrow. Be looking at as many of these as you can, and we will do some more of these tomorrow. We'll start the review and we'll continue it on into Thursday, and Friday's optional if you want to work some more problems. So questions, anybody?
I have a question.
Yes.
So when you got y equals 36 over x squared, and I don't understand what you did. I don't know how you got c equals 24x squared plus 36xy. How did you turn that equation into the next one?
Here's how I did that. Let me get a different color here so you can see what I did. I solved this for y. So I had, you see how where I solved it for y, Haley? I just divided both sides by x squared, okay?
Yeah.
And then I went down here and I put that in place of y. I put in 36 over x squared in place of y. See how I did it right here? That's what y was.
Okay.
Do you see what I did?
Yeah.
Okay. I was trying to get the equation in terms of one variable. Okay. Work hard on this tonight and start working on your review sheet. We'll work some more of these tomorrow, and we'll start the review sheet and go for it here. Okay?
Okay.
All right. I will see you tomorrow. Have a good evening.
All right. Thank you.
You're welcome. Bye.
Bye.